to taste it. All right, so questions? All right, so drop your homeworks up front if you haven't yet. And we're going to jump into number theory today. So we did a bit of an intro to it yesterday. But let's start talking about number theory. And I might talk about some more induction tomorrow. I looked up something called the muddy forehead problem. And it's a really cool induction problem. So we might talk about that tomorrow. I posted your next homework assignment on Canvas, and the number theory homework comes from the other 215 text that's available on Canvas. So it's titled Additional CSE 215 Text. It's right below the main textbook. That's where your homework problems come from, because there's no real number theory chapter in the main text. So look in there for the homework questions. So let's start by talking about divisibility. And we're mostly dealing with integers in this unit. So you can always divide numbers, but we're talking about numbers that divide numbers evenly. 6 is divisible by 3. 6 is not divisible by 4, right? Because it would give us a fraction. So here's our main definition. Given integers a and b, we can say the following. A divides, bless you, A divides B if there exists some other integer such that B is equal to A times that integer. This also means that B divided by A is an integer, because B divided by A is just C, and C is an integer. So A divides B if, when you take B and divide by A, you get an integer. So it divides it an integer number of times, basically, is what we mean by divides. So 2 divides 8. 2 does not divide 7. Right, everyone clear on that setup? Okay, so equivalently we can say A is a factor of B. And equivalently we can say B is a multiple of A. X. And equivalently, we can write A vertical bar B. So this means A divides B. And this is really, 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 really important to look at. Because we're not doing a slash where we say A divided by B. This is a vertical bar. It's a statement that A divides B. B is a multiple of A. So we can write the following. 2 divides 8. We can also write 2 does not divide 7. Okay, this is just notation, but we're going to talk about divisibility a lot, so we want this shorthand. And somewhere late at night while you're doing homework, you're going to suddenly replace A divides B with A over B, and your proofs are going to go wonky. Okay, so come back to this. A vertical bar B means A divides B. But we can take the definition of A divides B as this. A divides B means there exists some other integer c such that B is A times C. And this is really all we need to start doing some interesting things with divisibility. So let's do some theorems. And the proofs we do in here will feel, in some cases, a little different from the proofs we were doing in chapter 3, where we had, statements and reasons for them and so on and so forth. But we'll also go back and visit odd and even numbers as part of number theory. So here's a theorem. So everything's going to be an integer, so I'm not going to keep saying is an integer. So if A divides B and A divides C, then A divides B plus C. So we can think of this different way. If B is a multiple of A and C is a multiple of A, then B plus C is also a multiple of A. If A is a factor of B and A is a factor of C, then A is a factor of their sum. All equivalent statements. So how can we prove this? There's not a whole lot to do. We only know one thing, which is the definition of A divides B or A divides C. So A divides B is a premise. And the definition of A divides B means there exists some integer, I'll call it K1, such that B equals A times K1. So B is a multiple of A. That's definition of this divide symbol. We also know that A divides C because we're given that as part of our hypothesis. And since A divides C, there's some integer such that C equals A times that integer. It's not going to be necessarily K1. In fact, it's almost certainly not going to be K1, but there's some integer, we'll call it K2, such that C equals A times K2. And that's the definition of divides. Well, what are we trying to show? We're trying to show that B plus C is some multiple of A. So we might have a section over here that we say ignore. And we want to show B plus C equals A times some other integer. Well, we have an expression for B, we have an expression for C. We're trying to make some statement about B plus C. Kind of one of the first things you might think of is let's just add B and C in this form. So let's do some algebra. B plus C equals, this is this is B, and this is C. So that's substitution. And hey, we got an A, let's factor it out. That's factoring out A. And since K1 and K2 are integers, K1 plus K2 is an integer, so this is A times K3, where K3 is an integer, and that's properties of integers. And what have we just shown? We just showed B plus C is equal to A times some integer. That's the definition of A divides B plus C. And that's exactly what we were asked to show. So there's a nice formal proof that doesn't really take a whole lot of clever thought. It takes a lot of writing. But if A divides B and A divides C, we can add B and C together, and that's divisible by A also. So is everybody comfortable with this demonstration? You all believe A divides B plus C? And we can show a number of things similar to that. So here's a theorem. If A divides B, then A divides any multiple of B, any integer multiple of B. So if A divides B, A will also divide 7 times B, or negative 15 times B, or 436 times B. And we don't have to prove this formally, but you can see how this is going to work. A divides B, so B is going to be equal to A times some constant. And so B times C is going to be equal to A times C times some constant, which is just A times some other constant. Because an integer C times an integer K1 will give you another integer. And since BC is A times some integer, that's enough to say A divides B times C. So we have a second theorem. And here's a third theorem. If A divides B and B divides C, then A divides C. So this divides that, and that divides this other thing, then this divides that other thing. So could you prove this using the ideas of what we've been doing? Maybe, not at all. All right, let's go to the board. So find a group of friends and grab a marker and a space of board, and we should be able to have 7 groups, give or take. And think about how we did this proof. And see if you can do this proof. So you want to show this.
Yeah, I guess that's where we're going to mess up.
And I'm going to go on marker patrol and throw out all of our bad markers. That's not too bad.
Like a I think we I don't know if we're supposed to be doing this like really formally or not. I can't really
Formal enough to convince someone. So the third exists statement, so are you saying that's true?
This was kind of an extension. Oh yeah, that's working out. So yeah, the definition of what that is that's what we're proving. Yeah.
Okay, because that's what you're trying to show. But you got the right pieces below that.
So this would be our ignore block.
Yeah. Just that first part, maybe.
So how do we get to the pieces? So we're still plugging in. We're still plugging this in. And we're still plugging in. So it's
Yeah.
It's
Just not that, yeah, but I think you got to that last line legally, and that shows you that that ignore block is now true, which is, yeah. Okay, cool.
Is that bad?
No, that's good. Be careful, it's not always the same K. Right, if B is A times K, you can't assume that C is also B times K. Because B could be twice A and C could be 10 times B. Yeah. You can make up symbols, that's legal.
And that's it then? We can say QED after that?
Mm-hmm. Yeah, careful on that third statement.
Third one? Is bad?
Well, you made a change, so you gotta change something else in there. So A times K times Y equals C. Yeah. Not just K and Y. But you need more than just the fact that K and Y are integers. So write down your conclusion and see if it actually follows from that. All right, perfect. Cool. All right, so take another minute and wrap up, and then let's go through these. And most of them look like they're exactly what you want. What's your conclusion from that third statement?
That we have to have C bigger than A and B bigger than A and C
Okay.
bigger than B.
What are you trying to prove ultimately?
That A divided by C is going to work out to be an integer.
Okay, so does that follow directly from this third statement? What's the definition of A divides C?
That there's some integer A that goes into C and even the amount of times it's going to make an integer, right?
Okay, that wasn't exactly how we wrote it though. I don't have the definition up there anymore. Yeah.
If
So
A divides B, then A divides any integer. It's a multiple of B.
do you have the definition before we did the theorem?
Yeah, I got this one. If A,
Even before that.
oh, way up here.
You missed the definition.
Oh,
So A divides B means there's an integer C such that B equals A times C.
okay.
Right, and that's what you were using when you wrote that first statement. There exists an integer K such that B equals A times K. There exists an integer Y such that C equals B times Y. To show that A divides C, you want to show there exists another integer Q such that C equals A times Q.
Okay.
right? And you can get that from this third statement if you make one more comment on this, which is simply that k times y is an integer. Then you know that c is a times an integer.
So it's something that k times y is an integer?
Yeah. Right, and that's just the properties of integers. Now you know that c is a times an integer. That tells you a divides c, and then you're done.
That's it?
That's it. Yeah.
Great.
Cool.
Oh, okay, cool. So you still go.
Sneak by.
Ours is good.
Oh, you got football plays, cool. C is a times that, c is that, c is a that, c is that. Cool. Awesome. And you spelled out QED. All right, cool. So go ahead and take your seats again, and we'll talk about this. Did you finish this? C equals, okay, C equals a times K3. You're right. What's K3?
K3 would be A1 plus, K1 plus K2
Times.
times K2.
Yeah, yeah, perfect. All right, good, 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 good. Perfect. All right, cool. Yeah, so everybody got to this. So A divides B, which means B equals A times some integer. B divides C, which means C is equal to B times some probably different integer. And then we can substitute this B into here and say that C equals A times K1 times K2. And K1 times K2 is an integer. So C equals A times some K3, where K3 is an integer, therefore A divides C. That's the gist of it. So you can do a number of proofs along these lines, right? And all we're using is one definition. A divides B if B is equal to A times an integer. But we can nonetheless state a number of facts about this. And these particular facts are useful because of something which we're not going to prove, but we're going to state, which is called the division algorithm. And it's actually a theorem, it's not an algorithm, but for some reason it's called the division algorithm. And sometimes I state this very formally and it becomes this big page of symbols and long-winded statements, and I don't want to do that because it really loses the central idea of the division algorithm. Division algorithm is about using this modulus operator we have in C, this percent sign. It's looking at the remainder when you divide something by something else. Okay, so here's the way to think about this. So let A be an integer, and A is going to be called the dividend. Bless you. And let D be a positive number, which is called the divisor. So we won't divide by 0, we won't divide by negatives. So D is the divisor, A is the dividend. If you try to divide A by D, it may go in evenly, in which case you get an integer, or it may not go in exactly, in which case you'll have some remainder when you do your division. Right? So if you try to divide A by D, you may have some remainder. we'll call our remainder r. If there's no remainder, then r is just 0. Okay, so we can write our original number a equals a divisor times some other integer q plus some remainder. Q is an integer called the quotient. So a is the divisor times the quotient plus a remainder. We can always do that, right? If we have 17, let's say a equals 17 and d equals 3. So we're dividing 17 by 3. We can say 17 equals 5 times 3 plus 2. So 5 is the quotient and 2 is the remainder. We could also say 17 equals 4 times 3 plus 5, in which case the quotient is 4 and the remainder is 5. We could also write 17 equals 6 times 3 plus negative 1. Bless you. In which case the quotient is 6 and the remainder is negative 1. There's a lot of ways we can write a number as a product of a second number plus some remainder. Okay? But what we're doing is we're fixing our original number 17, and we're fixing what we're trying to divide by, in this case 3. And our goal is to write our original number as something times our divisor plus a remainder. And everybody sees that there's multiple ways to do this, right? 17 could be 0 times 3 plus 17. That's another way to do this. So let's enumerate some of these. So 17 could be 0 times 3 plus 17. Could be 1 times 3 plus 14, 2 times 3 plus 11, 3 times 3 plus 8, 4 times 3 plus 5, 5 times 3 plus 2, 6 times 3 plus negative 1, 7 times 3 plus negative 2, and so on. Thank you. It could also be negative 1 times 3 plus 20, and so on. So there's a lot of ways to write 17 as a multiple of 3 plus some remainder. But if we look at all of these remainders, for all the possible ways we can write 17 as something times 3 plus a remainder, there's a way to pick out a unique one of these remainders, which is to have the requirement that our remainder is bigger than or equal to 0 and less than our divisor. So our divisor is 3. There should be exactly one of these where our remainder is either 0, 1, or 2. And that's this one right here. The division algorithm is a theorem that says there's always one and only one way to write this where your remainder has this property. And that's not really that unfamiliar to us, because in a C program, if we asked for the value of 17% 3, what would it give us? It's going to give us 2. So the percent operator is doing this. It's looking for the remainder when you divide 17 by 3. But when we talk about this, we're usually talking about a remainder that satisfies this property. So go back to elementary school when you do division, and your teacher says, what's 23 divided by 5? And you say it's 4 with a remainder of 3, right? You could have said it's 0 with a remainder of 23, and mathematically you'd be correct, but you probably wouldn't get the gold star on your paper, right? So we're looking for how many times can we put 5 into here? As many times as possible, but not too many, right? And then what's left over after that? And the reason we don't write that this is 3 with a remainder of 8 is because we could have put more than 3 5s into here. We could put a 4th 5 into here, take us all the way up to 20, and then have a remainder of 3. So we've been doing this most of our lives when we divide integers and we look for a quotient and a remainder. But the division algorithm is a theorem that formally states that we can always do this, and there's a unique answer, which in this case satisfies this property, that the remainder is between 0 and 5, not including 5. The division algorithm makes it possible to talk about division modulo something, okay, and know that we're talking about a unique value. So when we say 17% 3, we're looking for an answer that's between 0 and 2. So if we talk about, 10 modulo 3, the remainder there is 1. If we were to talk about negative 10 modulo 3, that gets a little weirder. But it's the exact same definition. We may have to think about it a little harder, though. We want negative 10 is something times 3 plus a remainder. Okay, well, negative 10 is certainly 0 times 3 plus a remainder of minus 10. But that's not a value we want. We want a remainder bigger than or equal to 0, less than 3. So negative 10 is also negative 1 times 3 plus negative 7. Because this is minus 3, this is minus 7. That gives us minus 10. It's negative 2 times 3 is negative 6 plus negative 4. It's also negative 3 times 3 is negative 9 plus negative 1. It's also negative 4 times 3 is negative 12 plus 2. It's also negative 5 times 3 is minus 15 plus 5, and so on. And what's our unique value which has r in this range? It's this right here. So negative 10 modulo 3 is going to be equal to 2. So same definition, but we have to work a little harder with the negative. All right, so are we clear on what we mean by dividing one thing, looking at one thing modulo something else? All right, so A% D equals R means A equals some Q times D plus R, where Q is an integer, and R is bigger than or equal to 0 and less than the divisor. And most everything we do when we're talking about number theory is going to be related to this modulo operator, or can be expressed in those terms. All right, well, so let's have a definition. We say A is congruent to B modulo M to mean basically that A% M and B% M have the same value. They have the same remainder when you divide by M. And this is written as A triple equal sign B parentheses mod M. So that symbol there, A is congruent to B mod M, means A and B have the same divisor when you divide by M. And clearly we need to be talking about a divisor which is unique, right, between 0 and M minus 1 in this case. Another way to think of this is that M divides the difference of A and B. Because if A is this much more than a multiple of M and B is this much more than a multiple of M, when you subtract them, you're going to get a multiple of M. So we can say A is congruent to B mod M means M divides A minus B. It divides their difference. So for example, 18 is congruent to 11 modulo 7. And there's two ways to see that. 11 mod 7 is 4. It's 4 more than a multiple of 7. 18 mod 7 is also 4. It's 4 more than 14. But we can also see that their difference, 18 minus 11, is 7. That's a multiple of 7. So this and this are saying equivalent things. But this one's the definition that's, sorry, this is the one that's a little easier to work with because we have a formal definition of what divisibility means. So when we say A is congruent to B mod M, think of it like this. M divides the difference of A and B. All right, well, here's a theorem which you might think is obvious, and it is, but it wouldn't necessarily be in other settings. If A is congruent to B, then B is congruent to A, and this is all mod M. If A is congruent to B, then B is congruent to A. And we're used to things being symmetric like this. If A equals B, then B equals A, right? But not all things that we can put between two things work like this. For example, if A is greater than B, it doesn't turn out that B is also greater than A, right? But this looks like an equal sign, so we expect this to be true. But can we prove this? If A is congruent to B, then B is also congruent to A. And if we want to prove it, we've got to go back to the definition of what we mean by A is congruent to B. So A is congruent to B. So here's a proof. A is congruent to B, that's a premise. It's our hypothesis. And that means M divides A minus B. That's the definition of congruence. Well, what does it mean to say M divides A minus B? Yeah, exactly. So A minus B equals M times some integer, where K is Z. That's the definition of divides. And we'd like to show that B is congruent to A, which means we'd like to show that B minus A is divisible by M. Well, we know something about A minus B. What can we say about B minus A? It's just negative A minus B, right? So that's properties of negatives or integers or something. And this is equal to m times minus k, which is equal to m times k2, where k2 is an integer. Because if k is an integer, then negative k is also an integer. It's a different integer, but it's still an integer. And so we've shown that b minus a is an integer times m, therefore m divides b minus a. That's the definition of divisibility. Therefore, b is congruent to a mod m. That's the definition of congruence. So it feels like it should be pretty safe to say if A is congruent to B, B is actually congruent to A, but it takes a fair amount of work to actually show that. Because we can never just assume, well, that looks like an equal sign, and so I think you can probably flip those things around, right? All we've got is two definitions, definition of congruence and a definition of divisibility. But you can build up from there and show this third property now, which is that this congruence symbol is what we call reflexive. So it says we can switch the order of those things. Well, we can prove other similar things, and we're not going to, but we could. But here's something that will be true and will be really useful. So if A is congruent to B modulo M, and C is congruent to D modulo M, then A plus C will be congruent to B plus D modulo M. So for example, let's set m equal to 7. And 17 is congruent to 3. And, I don't know, 65 is congruent to 2, because it's 2 more than 63. So if we add these up, 82 should be congruent to 5. And what's 82 minus 5? 77, that's a multiple of 7. So in fact, 82 is congruent to 5. Now that's not a proof, but that's a demonstration of this theorem in one particular case. And you can prove this without too much difficulty doing just what we did in the previous proof. Right? Use the definition, show that A minus B is a multiple of M, C minus D is a multiple of M, add them together, and subtract in the right way, and you'll be able to show that this minus this is a multiple of M. And it's not too bad a proof. But this is what's really going to make the rest of this stuff work. Because it means that if we have two numbers, A and C, we can add those together, or we can take anything that they're each congruent to and add those together and get to the same answer. The same answer meaning answers that are congruent to each other. And what this is going to let us do tomorrow is take the infinite number of integers that we have, endlessly positive, endlessly negative, and if we're working, say, modulo 7, we're going to be able to take that entire set and reduce it down to a set of just 7 things. 0, 1, 2, 3, 4, 5, 6. And every number, we're just going to replace it with what it's congruent to modulo 7. And we're going to be able to say things about this huge number plus this other huge number by working with just these small numbers from 0 through 6. So we're going to reduce the infinite set of integers to a small set of what we call modulo classes. And we'll have a few of those, and it's going to make certain kinds of proofs really, really easy for us to do. Okay, so this is the key property that we're going to work with. We'll start from there tomorrow and see how we can use that to do some cool math.